And the speaker today is Dr. Marc Dupuis. He is a well-known figure, and he doesn't require much introduction. But even then, I will see you a few words. So he's a consultant specialized in the application of mathematical modeling for the aluminum industry since 1994. The year when he founded his own consulting company, GéniSim Inc. Before that, he graduated with a PhD in chemical engineering from Laval University in Quebec City in 1984, the year I also did my PhD, and then worked 10 years as a research engineer for Alcon International. So I will invite Marc Dupuis if he wants to say a few words, and then we will switch over to his presentation. Marc Dupuis, you'd like to say a few words?
Namaste. I practiced a little because I was in India 3 weeks ago. I stayed there for 2 weeks. So welcome to this conference. Okay. I will be happy to answer questions after.
Okay. So I'm not going on the full CV of Dr. Marc Dupuis, and this presentation is about 53 minutes or 54 minutes. So I will request IBAAS office to start his presentation, and this will be followed by questions and answers. So he will answer all your queries, and by the time more people may join, so you are all welcome. So Priyanka, please start the presentation.
Good afternoon. My name is Dr. Marc Dupuis. I'm working for my own consulting company, GéniSim. I will be presenting the March edition of the IBAAS 2026 Technical Lecture Series. The subject of my talk is modeling of steady-state cell heat balance, and then transient cell operation, specifically power modulation. Of my presentation is as follows. Introduction to all cell models. There's different type. My company is offering all the type I'm going to present. Then I will specifically discuss thermoelectric model or cell heat balance model. And the first one is a dynamic cell simulator called DynaMark that I've developed. Then there's a series of 3D and ANSYS model to use for design purposes. And after that, one of those ANSYS model will be converted into a transient for studying dynamic evolution of cell, specifically modeling power modulation, and then a little conclusion of the last part of the presentation. So this slide is presenting the 4 pillars of models that were used by AP and Imam Pechini to develop the AP18, then the AP30. So this slide was extracted from a Pechini presentation, and that was presented way before the development of the AP60. Obviously, AP60 was also developed with the support of those 4 pillar model. The first of the 4 pillar is the MHC model. That was very important to go from 180 kiloamps. Even at 180 kiloamps, it was a breakthrough to get the cell so stable. And then the AP30 increase of size, and then up to AP60. Without a good MHD model, it would have been impossible to develop so big amperage cell. Then the second pillar, the one that we will concentrate here this afternoon, is the thermoelectric model for the cell heat balance. And the third one is the mechanical model to design the pot shell. And the fourth one is the transient thermomechanical model that is required to be able to start up a big cell without damaging the cathode lining. So in this slide, we are seeing the main three model. So the first one illustrated here is the pot shell mechanical model. And this slide or this picture of that model is taken from my very first TMS presentation in 1991 when I was still working for Alcan R&D. So that one is to improve the design of the pot shell structure to prevent it to deform too much and sometimes even fail completely. So this, for example, this pot shell, as it was designed in the 60s, or was too weak and was breaking. And it was redesigned by making it stronger, and that was presented in 1991. The second one is the MHD, dynamic cell stability model, and that one, the model that I'm selling is called MHD Valdis. It is calculating the behavior of the metal pad and when the metal pad is amplitude, the deformation of the metal pad is amplifying, we are getting a wave that is getting so intense that we get a short circuit. So those conditions are called unstable cell condition. And to prevent that, you have to design specifically the magnetic field through the bus bar location and the metal current density field in the metal that you improve by having, for example, copper collector bar or things like this. So this can be studied, the stability can be studied in that kind of thermoelectric MHD model. And the last one is the thermoelectric cell stability, thermoelectric cell balance model that we will concentrate on that type of model in this presentation. When it's time to retrofit the cell, existing cell, we are concentrating on a subset again of those type of model. We have to deal with the wave instability. So this is an example of recording of a wave. And we have also when we're creeping the amperage, normally we have to design the cell appropriately, the lining design, so that the ledge is remaining at the optimum position. Too much ledge is not good for cell stability, as the ledge to get under the anode, and not enough ledge mean that we have a risk for having a red sidewall and eventually losing the cell through the sidewall. So those are the two main issues we want to address. So the stability of the cell, so the noise level or the intensity of the voltage fluctuation, and the second one is the solid balance to achieve a proper protection of the sidewall without having excessive ledge toe. And this is done to again the same two type of model, the MHD cell stability. So in my case, what I'm offering is the code MHD Valdis. And then the thermoelectric solid balance model that in my case are based on ANSYS. And I will start soon to display the full series of model available. So on the thermoelectric models, there are two big classes. They are the cell simulator. So Dynamark is the code I have developed that I'm offering for simulating the dynamic behavior of the cell, complete cell. And then there's those finite element based, ANSYS is the name of the software, models that are thermoelectric and are used to predict the anode voltage drop, the cathode voltage drop, the ledge profile, and the cell heat loss, total cell heat loss. So Dynamark description is as follows. Dynamark is a software based, the core is coded in Fortran. That is a scientific language for coding equation. So there's a set of equations representing the process behavior. So equation to compute the cell voltage and then the cell heat loss. In the mass balance also, because we are feeding alumina, we are making metal, we are adding other material, so changing anode. And there's the decision on when to move the anode to adjust the cell voltage. Is handled by the controller model, that is a coding of a cell controller, essentially. And then finally, there's an event. So there's an operator model where we decide when to tap metal, when to change anode. And all those three sub-models or part of the Dynamark are interacting with each other to be able to simulate the operation of a cell over a period of days or weeks, depending on how long we want to run the simulation. This slide presents specifically the thermal sub-model in Dynamark. That is a very important part of the software because we need to have a cell simulation that is fast, but at the same time is fairly accurate for prediction of the thermal response of the cell to event like increasing ACD or increasing amperage or having an anode effect. So everything that affects the thermal balance should be accounted for dynamically without having to compute forever, like it would be the case if you use a more a bigger model like an ANSYS-based finite element model. So this one is called lump parameter because it is representing essentially the main lump or mass of material is the liquid zone. So both the metal and the bath that are considered to be at the same temperature, T up. And we have 4 ways for the heat generated in that mass to be dissipated. Through the anode panel, through the cathode bottom panel, and through the side ledge at the metal level and at the pad level. And to represent this, you have to calculate some resistance and heat flux. So the heat flux through the anode is one variable, and through the cathode bottom is one variable, and 2 more heat loss through the ledge at the metal level and the heat loss through the ledge at the pad level. And those are computed by solving a set of equations. And in the lump parameter plus, that is a new a version of the model that was developed over the years, I'm solving 1D diffusion through the anode, through the cathode, and through the ledge at 2. So I'm not solving only the temperature of the liquid zone, but now I'm solving in this thermal model, I'm solving n equation for the dissipation of heat through the anode through a 1D diffusion equation, and the same for the cathode and the same through the ledge. So I'm solving for n equation, n being the number of nodes that you decide to put in along the lines. And this is required to be able to get the proper response of thermal response of the cell. But before implementing that most advanced version, I was already in 1996 presenting a result from Dynamark for a cell that was a Soderbergh cell operated in Brazil, Aratu, Brazil. And this is the prediction of the operation of that cell for a period of 3 days. And we can see that that cell was having a lot of anode effect. That was typical operation at that time. So every time you have a red bar here, you have an anode effect event. And this occurring over time every about 4 hours, if I remember well. You break the crust to feed alumina, but you don't feed enough, and eventually the cell get to an anode effect before a feed cycle. And this was kind of required to maintain prevent the sludge to accumulate too much in the cell. And so this is the prediction of the simulation. Here we have the comparison of some measurement that were taken in 84. Is it 84? I forgot the year it was measured, but that was presented in 96, the comparison. So we have measurement that we're taking in Brazil. We have here 3 anode effects that occur. I think those spike at the high temperature. And we also see the measurement taken between anode effect. So you can see there's a ramp coming up and then there's a drop. And this is when the breaking of the cross occur. And so you can see that the code is representing well the behavior, not exactly that timing of the anode effect, but when we have an anode effect, we have the same thermal response. A second validation was done and presented in 2007. This time it was a cell that was operated in Germany that was measured by VW that merged with hydroaluminium. So this presentation was done by hydroaluminium, bought Dynamark. And so they provided me some data of a cell that had on purpose was instrumented and was put in total power failure. So they cut the amperage for 3 hours to measure the thermal response of the cell. And so that the data that was given to me, and then I did the simulation of that cell, and then the red is the measurement and the blue is the prediction of Dynamark, the most recent version of of Dynamite. So now I'm shifting to 3D steady state ANSYS based, so finite element based thermoelectric model. This first one is the F anode model. So the F anode model is accurately predicting the voltage drop through the anode, representing correctly the contact resistance between the cast iron and the carbon using a user-defined contact resistivity. And to be able to predict the contact resistivity directly, you need to go to a thermoelectromechanical model that are not is not the subject of this paper. And it calculates accurately the anode panel heat loss, calculating the heat loss of that half anode and then multiplying by the number of half anode layers on the cell to get the total heat loss of the anode panel. Now, the opposite is the complementary to the anode is the cathode slice model. So it is a cathode side slice model representing typically half of a cathode block with one collector bar if there's two, or only half of one collector bar if there's only one bar in that cathode block. You have all the lining, and you have the pot shell and the half cradle. And so that model calculate accurately the cathode voltage drop, calculate correctly the pot shell heat loss, so the heat loss from the pot shell and the cradle to the surrounding air, and it calculates accurately the contact resistance between the bar and the cathode block. Again, using a user-defined contact resistivity. If you merge the two, you get the full cell side slice model. So half an anode and half a cathode block put together, and this type of model can be used to converge the cell heat balance, because it will compute the heat generation and will compare to the cell heat loss for the operating conditions that are specified by the user. So the user decide on the amperage, decide on the ACD, decide on the anode cover thickness as a parameter to the model, and then the model will calculate the heat generated by those conditions, and will calculate the anode heat loss and the cathode heat loss, and will calculate the total heat loss. And then if it's not matching, it will change the superheat of the cell, like a cell will react naturally, and either increasing or decreasing the superheat and adjusting the ledge thickness accordingly to dissipate more or less heat, depend on the offset between the calculated heat generated and the calculated heat loss for a given iteration, and will converge to the steady state condition with the steady state superheat and corresponding ledge thickness and ledge profile. So this is the most convenient or useful model to use because it's doing all the work automatically. If you use a half anode and a separate cathode, half cathode side slice, you have to have a software, independent software. So it could be HS Salvolt, or it could be Marc, or another model that would calculate the cell energy produced, and then your user must add the heat loss of the anode and the heat loss of the cathode that the user specified superheat, and then compare with the internal heat calculated separately, and then adjust the superheat of the cathode until the total of the anode and cathode heat loss match the calculated cell internal heat. So this must be done if it's separate by the user. So the user is then have to converge itself. And if you use this full cell slice, then the model will do all the work automatically. The next model in complexity is the cathode corner, or if you extend full quarter. So the cathode corner, like it is displayed here. Here we have a corner model with only two cathode blocks. And what is important for this type of model is to predict the ledge profile in the corner, and also to get the heat loss of the end wall. That if you only solve for the cathode side slice, you don't have any idea of the prediction of the ledge profile in the end or in the corner. And it is at one point it is important to know not only what's happening on the side, but also what is happening in the end, and also the corner that could be over insulating or under insulated, and could be well, typically it will be under insulating. It will lose too much heat in that corner because you have two face to dissipate heat, and that the ledge in the corner will get too thick, and so you can correct by having more insulation in the corner. And if you overdo it, then it will be it will be over insulating the corner, and then you will lose the ledge there. So you have to have a balance, and that's why you need to study that kind of corner heat flux using a corner cathode model. You have the equivalent for the anode panel. You can have a corner or a quarter anode panel. So you can have, like here, 3 in the corner, or you can have the full quarter. And here, what is you gain as additional information is the heat loss through the end wall channel. That is that much, but it is important to be accounted. The next level is the full cell quarter here, displayed here. So you merge the anode panel, that could, in this case, the full quarter anode panel and the full quarter cathode, to get a full quarter cell. And this one, there's no need for any extrapolation to you solving really 1/4 of the full cell. And if you assume it is symmetric, because you neglect the effect of the flow, or you neglect the effect of the uneven position of the bad metal interface, you have you solve for this quarter and then you multiply by 4 and you have the total cell heat loss. So this is of course very accurate, but it typically take a lot of hours to solve. The next level of complexity after that, it is here we have a full half cell, and the justification to get to the half is that we have added the bus bar that is not symmetric. So the bus bar can pull current if it's not perfectly balanced, pull more current on the upstream or downstream side, or not perfectly equally for each collector bar. So this then creates some asymmetric in the solution that we can solve here. And in this model here, we have the liquid metal and liquid bath was added, not for the purpose of solving the steady state heat loss, but to be able to calculate the current density on the metal pad, considering the pickup of the current from the bus bar. And then the fact that the bus bar is there can also influence the cell heat loss by a paper that was presented recently by Hatch and myself, is that the bus bar is there having an effect on the radiation dissipation, and that this creates some asymmetry in the solution. Then the next level would be to consider the flow, and this was done also by merging data obtained from MHD Valdis with an ANSYS thermoelectric model like this one, where the heat transfer coefficient along the perimeter of the ledge is proportional or affected by the intensity of the flow. So then the final level of complexity for a thermoelectric cell heat balance model is the full cell model, like this one. And this very specific model is the one I presented of a design operating at 740 kiloamps. So there's 9 riser to that cell that is quite long. So a model like this will predict the current density in the full metal pad if the liquid zone is added, and will predict the total cell heat loss in the ledge profile based on the metal flow if you add the metal flow to define the heat transfer coefficient between the metal and the bath and the ledge. In the opposite direction, you can want to be able to solve quickly something. So this is the fastest complete model that you can have. It is a 2D plus full cell slice model. So this one is predicting the anode voltage drop, the cathode voltage drop, the anode panel heat loss, and the cathode heat loss very quickly, about 6 times faster than a full 3D cell slice. But is predicting everything almost as accurately, because the plus for the 2D is because those lines represent beam element or 1D element that are used to represent the stubs and the stub and the yoke and the stem and the collector bar. So it's 2D for the anode and the cathode lining, but it is 1D element are added to represent the elements that are not really representable in 2D. They are the collector bar and the stub and the yoke. So this once it's developed, this model can be compared to 3D, and then we can observe that it's very accurate. It is solving much faster, and this is not so useful for steady state because we are getting very quick steady state in 3D. But it is useful because this can be then extended to run in dynamic mode, so transient solution, so adding the time as a variable. So this is the list of the advantage or what the 2D full cell slice can do it is fairly accurate to predict the anode voltage drop, the bus bar voltage drop, so the cathode voltage drop. It is well representing the contact resistivity issue from the anode side. The cathode side is converging the ledge, and it is computing the cell heat loss. All of this very quickly. This table is a summary of everything I tried to said about different. The classic I have not presented. It was presented in the original TMS paper. That's what was done before I developed 3D and 2D plus models. So the issue of time is important because the last one I'm gonna convert into a transient, and then we don't want to wait forever for a transient solution. And so we have Dynamark that is very quick, but the Dynamark is not as accurate as the 2D transient model. So this is now the same model, but extended to be able to compute the dynamic evolution of a cell. So all the equations from mass balance that are part of Dynamark have been migrated to ANSYS. So this then extended 2D plus full cell slice is now transient. It is solving for the addition of alumina, the mass balance, the production of metal, the response, thermal response of the cell if you adjust the ACD, if you have an anode effect eventually, or if you lost power. And this is the model that will be used to compute the power modulation event in the coming slide. So it is a 2D plus thermoelectric. At the time it was first presented, it was running on the Pentium 2. And to solve 1.5 hour of 1 hour of operation, it took more than that to solve. So 1.5 hour of CPU time to compute 1 hour operation, using 2-minute time step to make the calculation. And that computer was now would be considered as a very fairly slow computer. And that was that calculation was performed in 1999. So here I'm presenting the animation of this 2D plus transient model for normal operation. So that means you have feed cycle, and there will, since it's 1 hour of operation, we have a few feed cycle, and those feed cycle create some fluctuation on the temperature, operating temperature, and we can see a little response in the lining. So it's very slight, so it's not obvious to see, but there's some fluctuation of the surface temperature of the cathode block and then the anode and the ledge that respond to the operation inside the cell. So this first one is showing the full temperature in the cell, and we can animate the response. That is a very slight response for this type of full-scale temperature. One thing is sure is that nothing happened on the outside. The fluctuation inside will never reach the outside. So we don't see, if we measure the heat flux on the pot shell wall, the feed cycle is not showing on the heat flux. It is completely absorbed by the lining itself. We need a major event to get the response from the outside surface. To highlight this fact, this is this now it's displaying, will display when I will start animation, the change of temperature from the initial steady state, or the initial temperature, and you subtract the change. So after sometime, yes, there's a slight change of temperature. You subtract that new temperature from the initial temperature, and then you get an offset. So a change of temperature between the starting point and the a given time in the simulation, and you will see that now the response will be more visible. But still, there's almost nothing. If you get to the very end, you see that the red point here is that there's a change of 1.8 degree that occur here on the slope of the ramming paste. The ledge has been removed because the ledge is moving, so that's confusing the calculation, because we need to have a fixed point in space and then compare the temperature from the initial to a temperature after some time. And the node that are moving cannot be used to make this calculation, so they have been removed here. So we can see that one point got colder, a bit colder here, and then this point here, maximum temperature offset of 1.8 degree over this hour of operation. And then so we can see that it is changing slowly depending on the feed cycle. Now there, we can see that present the result differently. We can present the evolution of, here is the bulk temperature, so the bath temperature over this 1 hour. So we have a feed cycle. So the temperature was going up and then going down during the feed cycle. And then we are, so this is the result of the 2D plus ANSYS model. And the other three curves, two of the three are on top of each other, but there's three curves there, are three versions of Dynamark with improvement of the thermal model. So from a pure lump to a addition of some 1D diffusion and further improvement to get to the most accurate version of Dynamark thermal model. So we can see that the Dynamark is predicting similar behavior but not matching perfectly the 2D plus model. This is for the temperature for 1 hour of normal operation. And the next set of curves for the evolution of the ledge thickness at metal level. For ANSYS, it is not a single value, it is an average. So this is an average of the thickness, because there's a variable thickness over the height of the metal pad. For Dynamark, it's a single number. And where you can see here clearly there's three prediction of the Dynamark based on the three thermal models or three versions of the code. And we have the thermal, the fluctuation of the 2D plus model that are fairly similar but not identical in here. So this is for normal operation. Now the next one will be a total power failure. So now we have the same model, but instead of running normal operation, so keeping the amperage that is 300 kiloamps for the full 1 hour and then having only the full feed cycle to get a thermal response, here we are totally stopping the cell amperage, so the cell is cooling down. As for the validation that was presented in 2007, but this time on my demo model, not on the cell that was stopped in Germany. So here we can see the response, thermal response is that it is the red disappear. So if you start from the starting, we have a red part here that is temperature over 970, and after 1 hour of the shutdown, we have lost that red, so the cathode is starting to cool down. And again, this is the full, and the ledge is getting thicker. That's maybe not obvious. If we see the ledge getting slowly thicker. So if we start from the beginning and then I go slow, then we can see the ledge increasing thickness as the cell is cooling down. And so this is showing a full-scale isotherm. Next will be to show only the offset of temperature from the starting point. Now it's cooling down up to, it will cool down up to 28 degrees. So one point at the end of 1 hour will be 28 degrees cooler than it was initially. And we have this again. So it is always the fastest response, thermal response is on the ledge where it is thin. So the thinner part of the ledge profile, it is here close to the toe. And then that part has already changed 28-degree cooler after 1 hour of power shutdown. But then the full cathode surface is about 10 degrees colder, and the same for the anode. But obviously there's nothing visible for on the outside surface. This is why trying to control the internal temperature of a cell from the outside is not possible, because there's at least a 6 hour, if not 12-hour delay between what you can do inside, what is happening inside, and what you can measure outside. And so inversely, if you change the boundary condition, or you change the condition of the outside, it will take 6 to 12 hours to reach the inside and try to have an effect on the ledge thickness, for example. So it is impossible to control a daily event of power modulation from the outside. And this was well known from the time of the simulation in 2001 already, and even before, because this was measured. So this is the thermal response of the total power failure. And here we have the curves, the cooling curve, so that from the 2D plus model, and then the 3 cooling curve from Dynamark. And obviously the most recent version is the most accurate, but it's still not perfectly matching. And I've not tried to improve further this since the publication in 2002 of this paper. But in 2007, I did this exercise where I matched the measurement, so it is possible to match the measurement. But until you have something to match, there's no point trying to, because the 2D plus model was not validated either. So the assumption was that the 2D plus is more accurate, but until you have actual measurement, it wasn't for at that time in 2002. I did not work more on trying to match those two models. But after 2007, I was able to match with Dynamark the measurement of a cell cooling down. This is the evolution of the ledge thickness at the metal level. So here we can see that the 2D plus is here in that curve. And then the two initial version of Dynamark were over predicting the motion, and the last version was under predicting compared to the measurement of 2D plus. So it means that I passed. There's still enough set between the two. That's why I'm saying 2D plus, it's way more time to compute, but you can expect it is more accurate. But now I've reached the point where I'm modeling actual power modulation. So this one is a 1 hour decrease of 50 kiloamps. So 1 hour of normal operation at 300 kiloamps, 1 hour at reduced operation at 250, and back 1 hour back at 300 kiloamps. So the 3 hour of simulation here, thermal response. So we start normal operation 1 hour, we have a power modulation minus 50 kiloamps, and then back to 300. So we have a cooling down from initial, and well, initially it is red like this, so that the cathode surface, we have a cooling down period because of during the power modulation, and then we are back to 300 where we are getting a return to the initial temperature after an hour of back to 300 kilohertz. So if you look at the offset of temperature, then we have the yellow is when we have like 1 degree or 2 degree difference on the cathode surface offset, and then after that it's going back to less than that. So if I move this bar, we go from initial all red, mean that's no offset because it's the initial value. Then we have 1 hour operation where nothing happened because it's normal operation. And then we have the beginning of the modulation, so they decrease at 250. And then during that time, the cathode responds by going down. Now the scale is very different from the total power failure. So at one point we have the maximum amount of yellow. That means that we have reached here the end of the modulation, the end of the operation at 250, and we have cooled down the surface of the cathode and the bottom, the face of the anode by a bit like about 2 degree, and then we are back to 300, and so we have then the temperature get back to almost the red. That was the initial temperature, except for the response around the ledge. There's still a minus 10 degree there. That will take more time to recuperate. So here we see the cooling curve. So 1 hour of normal operation, 1 hour minus 50 kiloamps, and then 1 hour back to normal operation, or full 300 kiloamps, so that the recuperation time. And after that 1 hour of normal operation, we're still far from being back to initial condition. And we can see the three response from the three version of Dynamark and the response from the 2D plus. For the temperature and the ledge thickness. So the first two are off, when the third version, the final version, is quite close to predict the evolution of the ledge thickness. So this is a simulation of power modulation using two tools, Dynamark and the 2D plus ANSYS thermoelectric. So as final exercise, I will present something that people are not maybe aware that is possible to do. I will modulate again 50 kiloamps, but this time I will correct the ECD to maintain the same heat generation. So I will give away some power because but not all of the reduction of the 50 kiloamps will be given away, because I will increase the resistance of the cell by increasing the ACT. The aim is to get no thermal response of the cell. So if you have enough bad volume and you want to waste your power by making heat to avoid cooling down the cell during that modulation, there's a way by increasing by 2 centimeters the ACT. And this is a simulation of this that I also presented in 2002. So this is the power curve. So this is the operation at 300 kiloamps. You give away 50 kiloamps, but at the same time you increase the ACT by 2 centimeters. So you're operating with less power. So this is the offset you can get to the grid, or that you have to pay only for this amount instead of the full amount during the peak hour when the power is more expensive. And you operate this way for 3 hours, and then you go back to the initial operation. So this is the power curve. The next one is the cell voltage, cell pseudo resistance curve. So this is the initial cell resistance target, adjustment of ACD here with at the end of the cycle. And you have enough set of target resistance to have 2 centimeter more ACD. You operate during the modulation, so at this resistance, and then you go back to your initial target to get back to your initial ACD. So this is the thermal response. As you can see, it's completely invisible to the power modulation. All you can see is the feed cycle. That means that I have completely compensated the for the reduction of amperage by an increase of cell resistance to maintain exactly the same cell internal heat. There's the penalty for doing that is in the next slide. The penalty is in the cell energy specific energy consumption that was already quite big because that cell, my demo cell is from a VAW 300 kiloamp cell developed in 1992-93. So it is operating with a lot of ACD. So it's not very efficient in terms of energy consumption. But once you modulate, it's even worse because it's 0.25, about 0.25 more. So you go from 13.75 to 14. So that's because you're making less metal, but you're wasting the same amount of heat. So that's why you're proportionally it is the worst. But this is the gain is that there's no thermal impact of power modulation, but at the cost of producing at a much higher specific energy consumption. The conclusion are that you can study thermal event 2 ways with Dynamark that is very quick and can then simulate long period of time, even month of operation very quickly. You can simulate a lot of events. You can do similar work with ANSYS 2D+, but it will require a lot more CPU time. Both can be used to study power modulation event. One event was produced and compared between the two, and the second event was done only with Dynamark. And it was demonstrated that it's possible to give 16% of the power of the smelter without having any thermal balance effect. Thank you very much for your attention.
Thanks, Dr. Marc Dupuis. And now this was a very interesting presentation, although I understand very little out of this. So I will open for discussion. And please, can ask question to Marc Dupuis. Please, welcome. Yes, please. Give your name. Yeah.
Nanduri Murtirasu.
Yeah.
In one of the slides, it is written that QFR bath, QFR metal, and QFB something. What FR stands for?
Like the slide when I was showing the heat balance calculation from Marc, there's a 4 equation. Q is mean for heat flux or heat loss. Capital Q normally is for heat loss in kilowatt, and small q is heat flux in kilowatt per meter square. So heat flux, heat loss and heat flux. So capital Q mean heat loss in kilowatt. So there's 4 equations because there's 4 ways to dissipate the heat from the band through the anode up. and from the metal through the cathode down, and then through the ledge at metal level, and through the ledge at metal level. So there's 4 equations and 4 value of heat loss, and that the total heat loss is the sum of the 4 equations.
Okay. Okay.
And in the paper, TMS paper that is available on my website, you can see the equation themselves are presented.
What is the
Mr. Das, yes.
what is the specialty of Dynamar? Is it similar to NC's?
No, completely different. It is ANSYS is finite element. So it is you have the distribution of the flux through the space. You have to remove your sound because you have feedback. Okay, so
I've got one more question. Heat, circulating heat loss, heat is 622 kilowatts, you said, and heat loss is 621 kilowatts, you said. Total input is that total is some of this heat.
At the end, when I was presenting the power curve, it is the power is the amperage multiplied by the voltage of the cell. So that's the electrical power provided to the cell. And after that, I was presenting the evolution of the cell resistance, the pseudo resistance. And in that calculation, I'm giving 16% of the power of the smelter. So I decrease the amperage of that smelter from 300 kiloamps to 250 kiloamps. But at the same time, I'm changing the target resistance of the cell. So I'm increasing the ACD by 2 centimeters to generate exactly the same amount of heat, because it's R square I, and the I is reduced by 50 kiloamps, but I'm increasing the R, the resistance of the cell, to compensate, to get the same heat generation in the cell at a lower amperage. And because I'm totally compensating, the power to the grid is reduced by 16% because I'm making less metal. So the energy to make the metal is reduced, but not the heat loss. Heat loss remains the same. And as a consequence, the specific energy consumption is jumping up from 13.7 to 14. So the smelter will be less efficient in terms of energy consumption, but it will be able to give to the grid 16% of its power without having any thermal impact. And obviously, you can make a partial compensation instead of a total compensation if you don't have enough BAT to make, because it's a big increase of ACD, you may not have enough BAT volume to increase so much. It's very risky because if you start to approach the point where the anode will get out of the BAT, then you will get you cut your circuit. So I'm not saying this is actually technically, well, theoretically you can do that, but it may be practically may be risky, or it may be impossible if you don't have enough BAT volume to open so much the ACD.
Okay, Martina, please.
Thank you. Hi, I'm Martina Messuti from Italy. Thanks for the presentation and for describe all the model. Very, very interesting. I'm a modeler, so I'm really interested about that. I have 2 main questions. The one is related to the approach. So I would like to ask you why you choose a finite element method to describe the cell instead of a finite volume method. I ask you because I'm more familiar with the second approach.
Finite volume is for normally for flow, CFD, computational fluid dynamics. For thermoelectric, or especially for mechanical problem, ANSYS was developed initially. Finite element history of development of finite element was initially developed for mechanical problem. So it's a structure that you want to analyze the mechanical response to a structure, you use finite element. And for thermoelectric, yes, you could use either method. They are equally valid, but ANSYS is the software that when I finished my PhD, I developed my own CFD model, and I was using finite volume. Or I even finite difference at the time. It was not even finite volume; it was finite difference with fixed Cartesian coordinate. So it was fine. It's called finite difference, not even finite volume, because volume you can have different shape of the volume, but the finite difference you have to fix the Cartesian coordinate system. But then I joined Alcan, and it told me, oh, go learn ANSYS. That is a finite element software commercially available. And I developed all my modeling thermoelectric on ANSYS. So there's essentially for thermoelectric, if you could use I don't know, Fluent or FIDAP or CFX to do the same kind of calculation. It will produce the same result.
Okay, thanks. If I can ask you also, because if I understand correctly, in one of your latest model, when you have a full cell or half cell, you model also the buff inside the cell. So I would like to ask you, what are the main phenomena that you take into account? I know that the current, I also the magnetic field. I would like to ask you if you take into account something else, such as bubble movement, convection, or something like that.
No, the model. I talked in the introduction about MHD model. That is MHD Valdis, and MHD Valdis is a 2D shallow water model for the CFD. And so it's solving the flow in the bath and the flow in the metal in 2D, and calculating the deformation of the interface with shallow water approximation. The ANSYS thermoelectric is only solving to the temperature and the voltage. That's all that the ANSYS thermoelectric model are doing. And so there's no bubble, there's no MHD, it's no flow at all. And it is for the liquid zone, it's only solving for the voltage. So there's not solving for the temperature, because the way I solve the thermal problem, I'm applying boundary condition on the ledge surface.
Okay.
So I'm not solving for the joule heat production in the liquid zone. I'm only solving for I'm calculating the heat generation using the same equation I'm using in Dynamark. So it is it's solving the heat generation by an equation, and it's applying a boundary condition on the ledge surface, and it is converging the geometry of the ledge to reach the steady state condition, where the surface temperature is matching also the heat flux that I want to impose. So I'm converging on the geometry to have the right temperature with the imposed heat flux.
Okay, thank you very much. I'm trying to do something like that with Fluent, with a joint solver. I don't know if you're familiar with that, with volume method, but yeah, it's quite challenging. So yes, okay, but thank you very much for the information.
Thank you.
Okay, thanks, Martina. And Devanand Bhattacharya, please go ahead.
Yes, I am D. Bhattacharya, ex-Group General Manager, NALCO. Marc, you remember Bhatta?
Bhatta, yes, I remember you.
Yes, yes.
You
came in 2005.
I was in Yangon 2 weeks ago, and then we talked about you.
Yes, yes. My question is, did you have any model after how much power of what will stop? After how long power of? Zero, I am telling zero, from 300 to 0 or 180 to 0 kiloamp.
Yeah.
After how long time pot will stop? We cannot revive. Do you have any model for that?
Well, the model I showed, we have a 3-hour power stop. It is already close to the limit. And what I've not studied what is the actual limit, but there's many publication from VW, from 3MET is one interesting one. There's another one There's 2-3 papers at TMS presenting people that were able to survive 5 hours. So 5 hours is about the best you can achieve. I mean, survive 5 hours is very difficult to do. You have to be a lot of experience to handle what to do during the power failure to be ready to apply back the power, and then to be very safely. So you cannot put the full power on after. But I've not modeled that. I only have read paper about people that have done the work themselves. So it is very difficult to survive 5 hours. I was there in at the time it was Dupuis in 2008. They had a total power failure for they lost about half of the smelter. Some lines survived the power they lost. That was about a bit more than 3 hours, and some line was not saved, and some lines survived. It was on the limit of what could be. Then so that's the skill of the response. So the people in place, if they have been trained to do this, to know what to do, and I cannot quote what they need to be done. There's a lot of things that must be done to prepare for reapplying the power.
In ALCO, you have survived once 13 hours 0 in a span of 48 hours.
Oh,
5 hours, and in between 50 to 100 kiloamp in some 24 hours around.
24 hours. I know that Alcoa, they present a paper where they can put the cell in hibernation. I don't know what that means exactly, hibernation, but they say that they can hibernate the cell for a long period of time. But I'm not an expert for this kind of operation. I've been asked a lot of time to give advice on operation. I'm a modeler, I'm a designer of cell. I'm not the expert in operation.
Another question is, do you have any model about anode metal distance with current efficiency? Anode metal distance with current efficiency.
Anode metal displacement?
Distance with current efficiency.
The impact of ACD on current efficiency, this is your question?
Yes.
Yeah. There's a Lillibom model is predicting something, and then some other model are saying no impact at all. There's a Alcoa paper where I've done some actual fit of data. So it's not a physical based model, it is a fit of data, and they have produced it's Gary Tarsi have published that paper, and there's an equation or a slope for the impact of the ACD on current efficiency. When I know from knowing the numbers from EGA, for example, is that they were able to squeeze ACD a lot, around 2.5 to 2.8 centimeter only, so it's quite reduced ACD, and they kept about the same current efficiency. So 94, 95, 96. So in the range, they were able to reduce a lot the ACD compared to, like, say, 4 centimeter, without having to suffer too much from current efficiency. So
okay, thank you, Marc. Thank you for a very good presentation.
It's something that
Mr. Behra, Maheshwar Behra has some questions.
Yeah. My question is very simple. So we have developed so many models. Is any model suggest to reduce or to design the refractory lining, mostly lining, to reduce the heat loss?
Yeah, well, that's exactly the model I presented now. There's a cathode slice model or the full cell slice model. They are specifically designed to study the lining response to. So what you do is that you put in that model the property of the material that you want to use, like calcium silicate or semi-insulating brick, insulating brick, and you put the property of the material in the model, and you need to use the property after some time in operation, not the brand new material property what you can get from the supplier. what is important is to put the property of the material during operation, during exposed to the sodium vapor and exposed to the pressure of the operation, and then the model will predict the heat loss accordingly. And if you want to dissipate less heat, then you have to use a better insulating material.
Okay. Okay.
And
Okay,
normally,
thank you for your presentation, and it was. I was reading your papers in different magazines, but this is lively. Thank you.
The way that you design cell normally, Rio Tinto, I presented a very nice paper where they describe what they call design cycle. You measure cell in operation, current operation of the cell. You measure the heat loss, the heat balance. Then you develop a model that predicts the same behavior. Then you use the model to design a prototype. Then you build the prototype. Then you measure the prototype operation to verify that your model was accurate. And then you iterate. So from the first prototype, you have a better model because you have obtained new data from the prototype operation. Then you can develop a second generation prototype and eventually even a third generation prototype. And when you're very satisfied, then you can implement in the full pot line, and you repeat this as many times as you want to create the amperage up. There's a story about many smelters have done this kind of work. For example, to go from AP30 to AP40, or to go from AP18 that was 180 kiloamps to Mago, they are now at 250 kiloamps.
Okay. Okay, thank you.
Any more question? Anand Swarnkar, any question? Anand? Hello, any more questions?
Sir, I have one question. Yes, Anand.
Okay, Kumar. Yes. Please.
Yes, sir. One second. Hello, sir. Good evening. I am Karun. Basically, I am from process and operations. I've never been used to models. So, but we get the models from our teams. What do you think? As a process operation guy, should I learn how models work, or I should just take the models and I should follow the teams? What do you think?
Well, when I just been back to a 2 weeks training in Angul, and then I train people from operation to use a very basic model, not the one that I presented in this presentation, but a simpler type of model that are more accessible, let's say, to and then I recommend people to learn the physics, so how the cell responds. So, for example, one misunderstood belief that I try to destroy there in Angul is that you can control the temperature of the cell by the GTC. It is absolutely impossible to do. The GTC can control the gas temperature of under the hood by changing the exhaust rate of the gas. But that will change the temperature under the hood. But that temperature change will have no impact on the cell operation. The cell temperature will not be affected by the temperature under the hood that was measured by EGA. So because I can explain, but it's take too long to explain why it's not affecting, but it's not affecting even the change of 30 degree on the exhaust gas temperature from, let's say, 150 to 120 will not change the operating temperature of the cell at all. So you need to, I recommend that the people that are operating cell, that they have this basic knowledge of how the cell responds to different things, and then you can study that with some simpler model, and that are available, like HS Cell Volt is one of them. I have Smart, that is a software that is less expensive than Dynamark to study the thermal response of a cell. And I train people in Angul. They are very happy to have learned those models.
Thanks, Mark. There is a question from Pradeep Chaudhary. Pradeep Chaudhary, please. Mr. Pradeep Chaudhary.
1 minute. Yeah. Mr. Mark, thank you very much for a nice presentation. So I am Pradeep. We have met at Angul because I was working in Angul for quite a long time. And during the course of my working, we have met also. And I have just one question, rather a very open, innocuous question. The question is that whether your models can be augmented into the digital twins for pods.
Dynamart could be used as a digital twin. But to transform it, a dynamic model like Dynamart into a digital twin, you need to do a synchronization loop that could be done. It was something similar was done by Hydro Aluminium. Hydro Aluminium, they have a dynamic model that is may be part of Dynamart because they bought the source code of Dynamart, but they have their own dynamic model before that. And so they use a dynamic cell simulator and they synchronize it with a loop of you need measurement from the cell, so you have the cell voltage, but they also record the superheat by measuring the superheat at the frequent interval, and they measure the current on each rod at a regular interval, and they feed that information to a loop that is used to synchronize the measurement with the simulation. And what the tool that is used to synchronize is called a Kalman filter. It's comparing the prediction of the model with the measurement and adjusting the model state until the model match the actual measurement. And at that time, the simulation is now a twin. The model being synchronized with reality, you can call the simulation now a digital twin to that cell. So you have to do this cell by cell, obviously. So it's requiring running a simulation of a cell for each cell in your smelter.
Okay, that's really great news, because I was just wondering whether you have already done it. So it has been done in Hydro. That I understand now.
It has been done in Hydro using a software similar to Dynamart. Me, I was not involved in that kind of work unless, well, I know the thesis of the guy who did the work initially. So there's a thesis available on this type of work, and there's a patent. Hydro has a patent, but was taken in 2011, so it may be obsolete already or close to be obsolete. I mean, so anyway, this is work done by Hydro, and that can be reproduced, but it's not easy work because Hydro, they took many years of R&D to achieve this.
It will be nice if someone presents this in the IBAAS. It will be great if someone presents something about this in the IBAAS.
Well, I just presented a paper. I could present this, but it is Hydro.
No. I thought in IBAAS somebody presents how to synchronize for digital twin your model with digital twin. That will be great.
You have an expert. There's people, and many people have expertise to synchronize the process with the digital twin. Not for actual cell, but for wind turbine or many processes, they are easier to synchronize than the actual aluminum reduction cell. So the technology to synchronize is well known by GE, for example, other company. So
no, I mean your model, not exactly. I understand.
You need the model and you need the synchronization loop.
Yes,
is another expertise.
I was meaning your model, Marc model, actually. So that would be great. Okay, thank you very much.
Thanks. Good question. Thank you, everybody. If anybody else, more questions? No, thanks, Marc. And your presentation will be available on IBAAS website and also on YouTube. Anybody interested, they can contact us. And the whole presentation will be shared to all participants.
One thing I would like to raise is that the animation, when I was talking about showing animation, in my recording, the animation were there, but not in when you presented the animation were not presented. So there's my version at least of this recording as any animation are there. They are when I'm saying you get the response, temperature response. It is the animation showing in the in the presentation that we're not showing in the presentation here.
I know, I understand, but we are also running in YouTube. So this will be also available YouTube, the whole video.
So the YouTube, you will see the actual change of temperature.
Exactly. It will be the running model. Okay. Thank you, Marc, for the nice presentation, and it's very well received. And next presentation will be Binuta Patras. She was ex-NALCO, and we will expecting her to make presentation. And Marc, you are always welcome in IBAAS lecture series. And if you can participate in IBAAS conference, we will be all
it's not too early. It's too early. I will try to participate. Now, for me, it was more convenient this time, 5 p.m. for you, than 4, because it's otherwise it's very early.
Okay, I understand. No problem. Maybe we can see the recorded presentation. Okay. Thank you, everybody.
Thank you very much. Thank you.
Thanks, everybody. Bye.